This playlist collects together modules of the third and final Neurons and Neural Networks lecture. And in this lecture, we're going to focus in a little more detail on learning rules and some basic types of neural networks. So the two learning rules that we're going to look at are an example each of a supervised learning rule and unsupervised learning rule, probably the most common versions of those rules. Our unsupervised learning rule is an associative learning rule, the Hebbian learning rule, which was a mathematized version of Hebb's law. And then the supervised learning rule that we're going to look at was a rule that was developed in the 70s. We'll look at it in the historical context in which it emerged. And that supervised learning rule is called backpropagation of error. After we go through the learning rules, then we'll talk about some very basic types of connectionist models. We'll look at linear associators that were often called perceptrons. Then we'll look at nonlinear recurrent networks like Hopfield and Boltzmann networks. Then we'll look at nonlinear three-layer feed-forward networks, which are pretty common implementations. And then finally, we'll look at recurrent three-layer feed-forward networks very briefly. We'll end the lecture by talking about some of the strengths of connectionist models, and specifically how connectionist models look a lot like natural neural computing, even when you look at their strengths and weaknesses. So this is Donald Hebb. Hebb is the source of the most famous unsupervised learning rule. Recall that Hebb's law states that when a neuron stimulates another neuron at a time when the receiving cell is firing, then the connection from the first to the second is strengthened. Now, Hebb's law was first stated in a specific mathematical form by Stephen Grossberg in the 1960s. You can use Hebb's law to change weights. That is, to modify the strength of connections between individual nodes in a connectionist network by pairing input and output patterns simultaneously. Specifically, weights are strengthened relative to the degree of mutual activation and weakened relative to the lack of degree of mutual activation. So a simple Hebbian rule would look like something like this, where this is our weight between our I and j, and here's the mathematical function that computes how the weight should be changed. So we activate both of these nodes, and the activation of those two nodes will then strengthen the connection between them. An example of a supervised weight change rule is backpropagation of error. Backpropagation is intimately tied to the history of connectionist and neural network research. And so we'll do a little historical flashback to give you a sense of why it is that backpropagation was an important development. So work on connectionist type systems began as early as the 1940s. In 1943, Warren McCulloch and Walter Pitt wrote their logical calculus of ideas immanent in nervous activity. Now, this just basically talked about how neurons could implement binary digital computers, but it encouraged people to start thinking about computability using neurons as an inspiration. Interest in connectionist systems flagged until the 1960s, however, in part because you had to build a computer, and it was usually a special purpose computer. But among the major contributions that revived these systems came from Frank Rosenblatt. He wrote Principles of Neurodynamics. And in that book, he defines systems called perceptrons using a number and proves a number of theories about them. One theory that Rosenblatt proved was that perceptrons could learn to do any problem that you could program them to do, which was important in part because you were building perceptrons by connecting them up manually otherwise, and secondly because this allowed you to figure out how to solve problems without actually going through and breaking down the problem and developing a program for them. Now, Marvin Minsky here, together with Seymour Papert, really kind of stuck the knife in neural network research when they wrote this book called Perceptrons. Perceptrons could do a lot of interesting things, but they also failed to solve certain kinds of problems. And in Perceptrons, Papert and Minsky rigorously prove that perceptrons can't solve any problems that are not linearly separable. And what does that mean? Well, that means that they can't solve any problems unless the correct division of the weight space was a plane between one possibility and another. In other words, unless the problem space broke down into the right answers on one side and the wrong answers on the other, perceptrons couldn't learn to solve those problems. What kind of problems are like that? Well, any problem that you just can't simply draw a line and break no and yes into a straight line. So you could draw a line sort of like that maybe and divide up this supposed Bill Clinton ideal woman problem space. But you can't just draw a line across it. There's no place where you can draw a straight line and breaks it into yes and no exclusively. A sort of famous version of this problem is exclusive OR. So exclusive OR is a version of OR that we often use in English that says of a disjunction, either this one is true or this one is true. One of the disjuncts is true, but they're not both true. And so if you look at a problem space where ones and zeros are standing in for true and false, all right, then your x and or here, your XOR rather, function has these two falses and these two trues. And there's no way to divide up the space so that you get both trues on one side of that line and both falses on the other side of that line. You have to draw a curved line somehow. And hence, this isn't a problem that could be solved using perceptrons, linear perceptrons. Now, though they did prove this, there were assumptions, and these assumptions turned out to be very, very important. So you can get a linear associator or a perceptron to solve the exclusive OR problem if you have hidden layers. That is, if you have more than one layer, output layer, input layer, and a mediating layer in between, even of a single neuron, which is what I've got here. If you have that, then you can get the linear associator to solve exclusive OR. However, what Minsky and Papert suggested and did not prove was that it doesn't look like it's obvious how you would get a perceptron to learn how to do that. There didn't look like there was an obvious training rule. There was a training rule for relationships between input and output. But how would you know what the error was for these hidden units unless you'd already solved the problem ahead of time? Similarly, if you use nonlinear activation functions, you can solve it just using a two-layer feed-forward linear network like this. However, Minsky and Papert again suggested but did not prove that nonlinear activation functions wouldn't turn out to be very important. We'll pick this up in the next module then.